So let's discuss yet another example of a reversible cycle known as the Otto cycle. Now, just like the Carnot cycle, the Otto cycle consists of 4 reversible processes. 2 of those processes are isobolometric and 2 of those processes are adiabatic. So the reason that we study the Otto cycle is essentially to gain more understanding into what takes place inside certain heat engines known as internal combustion engines. And these are the engines found inside automobiles. So let's begin by looking at the following diagram. So this diagram essentially depicts the 4 processes that take place inside the Otto cycle. So once again, each Otto cycle consists of 4 reversible processes, 2 being adiabatic processes and 2 being isobolometric processes. So let's suppose our initial starting position is found at position 1. So when we go from position 1 to position 2, that is pathway A. So let's see what happens in process number 1. So the gasoline inside the cylinder of the internal combustion engine is compressed adiabatically from position 1 to position 2. So this first process is an adiabatic process. So notice the volume decreases and the pressure increases. Now, because we're dealing with an adiabatic process, that means the heat that flows into our system or out of our system is 0. So recall, according to the first law of thermodynamics, the change in internal energy of our system is equal to the Q plus the W. The Q is the heat flow into our system, and the W is the work that is done by our system. Now, because in pathway A, we're dealing with an adiabatic compression, that means the Q is 0, and that implies that the change in internal energy during this pathway A, during our first process, is equal to the work that is done by the surroundings on our system to compress our system from position 1 to position 2. Now, let's move on to process 2. So process 2 is depicted by pathway B. So we begin at position 2 and end at position 3. So the gasoline at point 2 is ignited and burned, which increases the pressure under an isobolometric process. So isobolometric means the change in volume during this process as we go from position 2 to position 3 is 0. So our volume remains constant. So notice what takes place. So let's examine once more the first law of thermodynamics that states the change in internal energy of our system during this process, during pathway B, is equal to the heat that flows into our system plus the work that is done on our system by the surroundings. Now, notice that because we're dealing with an isobolometric process, the change in volume is 0, so that means no work is done by or on our system. So the W is 0, and that implies the change in internal energy during pathway B as we go from point 2 to point 3 is equal to the heat that flows into our system. So this quantity is usually given by QH. So basically that means as we go from position 2 to position 3, heat flows into our system, and QH, amount of heat, flows into our system. So our pressure increases and the volume remains constant, and no work is done during pathway B. Now, let's move on to pathway C. Pathway C is depicted beginning at position 3 and ending at position 4. So notice what takes place. This is once again an adiabatic process, but now instead of compressing, we're expanding. So the gas expands adiabatically, decreasing the pressure and increasing the volume. So our pressure drops as we go from 3 to 4 and our volume increases. So once again, because we're dealing with an adiabatic expansion, the Q is 0. That implies the change in internal energy of our system is equal to the work that is done by our system on the surroundings. So the reason the work is done by our system is because our volume essentially increases. And finally, let's move on to pathway D, which is depicted beginning at position 4 and ending at position 1. So, once again, we're dealing with an isovolumetric process. So our volume remains constant. And since the change in volume is 0, there's no work done by or on our system. But heat is exchanged with the surroundings. And because our pressure decreases, that means heat must flow out of our system into the surroundings. So when we go from position 4 to position 1, heat flows out of our system, and we symbolize this with QL. So finally, the gas undergoes an isovolumetric process, and the heat is discharged into the surroundings, and the symbol that represents this discharge is given by QL. So the change in internal energy of our system is equal to negative of the QL. The negative simply means that heat is discharged into the environment.